In this video, I will walk through the examples from the 4-3-4-4 activity. I know on the schedule it may have said 4-3 or 4-4, but what we're going to do instead is review a little bit from both of these sections because they're both such important sections. Now to start with, the first part asks you to create a concept map for f of x equals 2 to the x and f of x equals log base 2 of x. And then to create a side-by-side chart that compares them. This is what a concept map would look like. And what I've done is I've written out for each of the two functions, their domain and range, what type of function they are, what their base is, and then a graph. Notice that for f of x equals 2 to the x, the domain is all real numbers. We could put any number we wanted for x, any real number. But the range starts at 0 but doesn't include 0 and goes up from 0, so from 0 to infinity. The base of this is the 2, and the type of function this is it's an exponential function. And then when we sketch the graph, we see that there's an asymptote at y equals 0, and we have these two specific points. When x is 0, y is 1. When x is 1, y is 2. When we move over to the log function, f of x equals log base 2 of x, we see that the range is all real numbers. And notice that that was the domain of the 2 to the x. And the domain is 0 to infinity, which was the range of f of x equals 2 to the x. We call this a logarithmic function or a log function. And it also has base 2, and we can see the graph. Notice that the asymptote is no longer y equals 0, but now it's x equals 0. And notice that we've got the point, instead of 0, 1, we've got 1, 0. Instead of 1, 2, we have 2, 1. And if I write these things side by side, we see that the base is 2, the domain and range swap, and the asymptote y equals 0 or x equals 0. Let's move on to some other examples. Before we do some other examples, just a quick review. This is so important when you're working with logs. You've got to be able to translate from a log to an exponent or an exponent to a log. So we have a base b raised to an exponent equals some value y. That y in a log equation is called the argument. So we read this log base b of y equals x. So the base is b, the exponent is x, and the argument, or the answer, is y. Also, we need to remember that log base 10 of y is the common log. So when we don't see a base written, it's implied to be the common base of 10. And when we see a log base e, because that shows up in so many science examples, we call that the log natural or the natural log. And naturally, the base is going to be e. So log base e is naturally the natural log. And then one last piece when we get to solving equations, when we have the argument written as an exponential expression, so y to some exponent, that exponent, this r, just falls right down from the argument, falls right down from the y. So those are just a couple review things to have in mind when we do these examples. Now the first thing we'll review is using the properties of logs to condense. So when we want to condense log of 50 plus log of 20, and those are both log base 10, right? What we're going to do is multiply, because the adding connects to multiplying. So we have log base 10 of 100. So then I think 10 to what power equals 100? Actually, that's 1,000, isn't it? Because 5 times 2 was 10, and then we needed 2 more zeros. Sorry about that. So 1,000. So 10 to what power equals 1,000? And that exponent, because when we do the log, we're looking for the exponent. And that exponent is 3. So we could simplify this to be 3. When I want to expand this natural log, I could start by seeing that that square root of x squared plus 2 is the same as x squared plus 2 in parentheses to the 1/2 power, right? So when I expand this, anything above in the numerator is going to be added. Anything below is subtracted. So when I expand, what I'm doing is I'm going to break it into the log of x squared plus the log, in this case natural log, of x squared plus 2, but that 1/2 falls down in front. So 1/2 natural log of x squared plus 2. And then anything in the denominator is subtracted minus the natural log of x plus 2 to the 9th. And then that 9, that exponent, falls out in front. So do you notice these exponents all become coefficients? And then, oh, I missed this one, didn't I? This 2 should come down in front. So we'd have 2 natural log of x plus 1/2 natural log of the quantity x squared plus 2 minus 9 times the natural log of x plus 2. If you want to really be sure that you've got this, then you'll try those examples from a blank page. Let's try this one more time. Log of y divided by 10. Just like in exponents, the dividing connects to subtracting. So when I want to expand this, I'm going to subtract the log of y minus the log of 10. Now when I'm expanding for each piece, so each term we have a y and a 10, we're going to have to write the word log out. When I'm condensing, I'm only going to write the word log once. Now for this example, we're going to use common logs or natural logs and a calculator to evaluate the expression. So the base is 13 and the argument is 18. So I could rewrite this as common log of 18 over the common log of 13, or natural log of 18 over the natural log of 13. And when you put that into a calculator, you should get this is approximately 1.1269 if I round it to 4 decimal places. So try that on your calculator. Make sure you can get that result. Condensing. So notice when I condense, I'm only going to be able to use the word log once. So it's a log base 3 of what? The whole thing. And these are subtracted, so it'll be the 36 divided by 4, which is 9. So log base 3 of 9, well, finding the log is finding the exponent. 3 to what power is 9? That answer is 2, right? Because 3 squared is 2. So log base 3 of 36 minus log base 3 of 4 is equal to 2. And here we go, expanding. We're going back and forth, right? So for number 6, when I expand, got log base 8 of 7, and it's multiplied, so I'm going to add the log base 8 of 5. So we have log base 8 of 7 plus the log base 8 of 5. You're going to guess what the next one is? Yeah, you guessed it. We're going to now condense these, right? So to start with, before I really get going with the condensing, I'm going to go reverse with these coefficients, and they become powers, right? So we'd have the natural log, let me erase those so that I can read them clearly and get them written correctly. We'd have the natural log of x squared plus the natural log of y to the 6 minus the natural log of z to the 5. So notice that those coefficients become the power. And next to condense these, I'm only going to write the natural log once, the log base e once. These are all added. So when I condense it, they're all written as multiplication. Nothing was subtracted. Oh, except, do you see I miswrote this earlier? So let me go back with that. I must have misread that. Do you see this, that it says subtract here? And I wrote it as add. Let me fix that so it doesn't leave anyone confused. This said subtract. So had it been plus, this would have been correct. But with subtract, I've got to put that z to the 5th in the denominator. So the whole thing would look like this. The natural log of x squared times y6 divided by z to the 5th. Can you use those same procedures to expand this one? We see that it's multiplied, so that means I'm going to add them. So I'd have log base b of x to the 7 plus log base b of z. Now this 7 falls down in front. So I get 7 log base b of x plus log base b of z when I expand those. Next example, we've got use the properties to condense. So if I condense this, it's subtraction. We've got x to the 4 y squared, right? So I can start by working backwards with those coefficients. And if it's subtract, okay, condense, I'm going to write it as just a single log. And we've got a subtraction, so it's divided by y squared. Do you see the connection here? The subtraction becomes a fraction bar. Now using common logs, the base is pi and the argument is 63. Then I could write this as log of 63 divided by log of pi, or natural log of 63 divided by the natural log of pi. Either of these two would work. And then when I put that into a calculator, I should get that it's approximately 3.6193. Now, if I'm going too fast, great thing about a video is you can pause the video to go a little bit more slowly, or pause it to write down what you want to write down, etc. Now this one's a quick, easy one because we don't have a sum, we don't have a difference. All we have is a power. So that 3 just falls down in front. So we get 3 log base c of x, and that's all that we have to do to expand this one. Now for the 12, it's a little more involved. So when we have the log of square root of 10,000 times x, we could write that square root of 10,000 times x as a 10 to the 4th x, and that 10 to the 4th square rooted is going to be 10 squared, right? So we could see that as the log of 10 squared square root of x. And then when we expand it, log base 10, right, of 10 squared plus log base 10 of square root of x. Do you see what, without even calculating it in a calculator, log base 10 of 10 squared is going to equal 2. Why is that? Log base 10 of 10 squared means find the exponent. 10 to what exponent equals 10 squared? So that exponent is a 2. So this log base 10 of 10 squared is just 2. So our final simplified answer is going to be 2 plus common log of x, or in other words, log base 10 of x. You know, we could write that a little bit more expanded by catching that this square root is the same as x to the 1/2. So we could also say 2 plus 1/2 log of x. And that would actually be a little bit more expanded. Next, number 13, we're moving so quickly, but pause if you need to. Use properties to condense. So when I finish this, I'm only going to have this log written once. Now I've got to notice that this 1/2 is going to distribute to both pieces. So when I raise that, when I bring that 1/2 in, it's like x to the 1/2, y to the 1/2. Those are square roots, aren't they? So when I rewrite this, we've got log base 2. In the numerator, we've got a square root of x, square root of y. And then when I subtract, get a fraction bar, and that's going to be an x plus 7 to the 4th power. So it's going to look like this. Solving the equation by writing like bases. The base is 3, the exponent is x. The argument would be 81. But what I'm going to do is try to rewrite this. This 81 is a 3 to the 4th power. So x is equal to 4. Now, anytime we have an equation, there's an equation. If you can rewrite it with like bases, that is going to be the best approach. Number 15, we can't rewrite the 2.17 as a, we can't rewrite that as a power of 10. But what we can do is rewrite this with a log, solve this one, express it in terms of logs. So what we would do is take the log of both sides, throw a log at it when the x is up in the tree. So when the x is up as the exponent, when the missing piece is an exponent, or in other words, when we're trying to find the exponent, what we can do is throw a log at it. So when I throw the log at it, what happens? That x falls right out. So I'd have x log base 10, common log of 10, equals log 2.17. Well, log of 10 is just 1. Log of 10 is just 1, so this log 10 goes away. And why is that 1? Because 10 to what power equals 10? That exponent would be 1. So the log of 10 is equal to 1. So we have x is equal to log of 2.17. If I put that into the calculator, I get approximately 34 hundredths. So the exact answer is log 2.17. The approximate is approximately 0.34. Now number 16, do you see that we could write this one using like bases? I could rewrite this 64 as an 8 times 8. So I'm looking for the exponent. 8 to the x equals 8 squared. So x will be 2. I could also have thrown a log at it. I could have done the log of both sides, and I'd get the same answer. E to the 5x minus 7 minus 3 equals 28,520. What I want to do to start with, because I can't just rewrite this with like bases because I have an e, what I'm going to do is I'm going to isolate the e by adding 3 to both sides. When I add 3 to both sides, I get e to the 5x minus 7 equals 28,523. And now to solve this, what I can do is throw a log at it. Because the piece we're missing is that exponent, if I take the log of both sides, I could use any base I want, but whenever there's an e in the problem, use the natural log. You could do the log base 10 or log base 7, log base 15, whatever log base you want, but our calculator is only going to do log base 10 or log base e. And whenever there's an e in the problem, the best approach is going to be natural log, so log base e. When I do the log of both sides, this exponent falls right out. So I've got this 5x minus 7 times the natural log of e. The natural log of e is just 1. And that's going to be equal to the natural log of 28,523. Natural log of e is just 1 because e to the first power equals e. So to solve for x, I'll add 7 to both sides. and then divide by 5. So the exact answer for number 19 is going to be 7 plus the natural log of 28,523 all divided by 5. And if you do put that into a calculator, you'd get the x is approximately 3.45. Number 20, if I want to write 80, if I want to solve this one, I could notice that 81 can be written with a like base. Whenever you can rewrite with a like base, you want to do that. So watch what happens here. 81 is 9 squared, so I'd have 9 to the 2x minus 8 equals 9 squared. And once I do that, if we've got like bases, a 9 and a 9, then the two exponents have got to be equivalent. So what I would know is that 2x minus 8 is equivalent to 2. Now it's just a simple equation. Add 8 to both sides. 2x equals 10 divided by 5 on both sides. So x equals 2. Be careful, because we've got to, with log, when we're using logs, or we're going to have to get in the habit of checking our answer to make sure we don't get an extraneous answer. That's an answer where we didn't really do anything wrong, but it just didn't come out. So if I check this, if I put a 2 in, we get 4 minus 8. 9 to the 4 minus 8 equals, 9 to the 4 minus 8 equals 9 squared. And I might think, wait, that doesn't work. So sometimes when we check the answer, we're looking for an extraneous answer. And for this one, when I check, it just shows me, oh, I must have done something wrong here. So let's check this again. 2x minus 8, and I know some of you already caught this when I was doing it, didn't you? 2x minus 8 equals 2, so add 8 to both sides. 2x equals 10. Why would I have divided by 5 there? Well, it's because I was looking at it and I knew the answer was going to be 5, so I just got carried away and sped ahead too quickly, because it should be divided by 2, right? I want to divide both sides by 2. I know some of you already caught that, so good job. Now let's check it again. 9 to the 10x minus 8 is 9 squared, so that does check out. So it's a good thing I stopped and checked the answer. Good idea with logs and exponents to always check the answer, because with logs, we could often get an extraneous answer. Next example. When we look at this, we can't rewrite it with a base of e. We can't rewrite this 29 with base e. But what we've got to do first is isolate the exponential term. So we've got to isolate the e to the x. So I'm going to divide both sides by 7. After I isolate, I'm going to throw a log at it. I'm going to take the log, since there's an e in there, I'm going to do the natural log, so log base e. So we have the natural log of e to the x equals the natural log of 29 divided by 7. And when I do that, that exponent just falls right down in front, right? So natural log of e is just 1. Because if I translate that into a log form, or I'm sorry, if I translate that into exponential form, we've got log base e of e, and that's equivalent to this exponent, e to what power equals e? Well, that's a clear 1, right? So this is worth just memorizing because we use it so often. The natural log of e is just 1. So 1 times x, it goes away. And don't just memorize it. Memorize it so you don't have to think through it and work it out each time, but also understand why. And the why is because natural log of e means log base e of e. And when we say, well, what exponent would I have to raise to this base e to get an e? It's a obvious exponent of 1. So we've got the x equals the natural log of 29 over 7. And if I got an approximation for that, then, it looks like I did some of these out of order. Some of the page must have gotten out of order. But that would be approximately 1.42. And for number 18, we get another example we can write like bases. So 7 to the 2x minus 4 equals 7 squared. Since we have like bases, the exponents must be equivalent. So we'd have the exponent 2x minus 4 equal to the exponent 2. Add 4 to both sides, and we have 2x equals 6 divided by 2, and we get x equals 3. Let's see what's next in this. We're going to jump back to 21. Did you see that this 1 over 27 could be written as a power of 3? So 1 over 27 is 3 to the negative 3. So we have 3 to the 3 minus x equals 3 to the negative 3. Write the exponents equal to each other. 3 minus x must be equal to negative 3. So the opposite of x equals negative 3 minus 3, so negative 6. So x is equal to 6. And if we check to that, it does work out for us. Number 22, we've got e to the x equals 9.37. We can't write them with like bases, so how do we get that x down? Throw a log at it. When we throw the log at it, that x falls right down. So we have x, natural log of e. Natural log of e is just 1. So we have x equals the natural log of 9.37. There's the exact answer. And the approximate answer, when I put that into a calculator, is going to be approximately 2.24. Number 23, we'll divide both sides by 7 to start with. And then when we have e to the 5x equals 1099 divided by 7. Don't divide that, leave it exact, because what we'll do to get that 5x down is throw a log at it. So that 5x falls down, the natural log of e is just 1, so 5x is equal to the natural log of 1099 divided by 7, and then divide both sides by 5. So on my calculator, I'm going to do the natural log of 1099 divided by 7. Make sure you put parentheses there to do that division. And then that whole thing gets divided by 5. So double check that for the exact answer that you're getting this in the calculator correctly. And that would be the x is approximately 1.01. Actually, I think that maybe on the calculator, this 1099 divided by 7 might come out even, so check that. Back to condensing logs. So for this one, to solve this equation, what we'll sometimes do is condense a log. These are all base 3. So if I write it as a single log, I've got log base 3 of x minus 8 times x minus 3. And then that's going to be divided by x. What I could do from there is then write it in exponential form. So this is the base 3. The exponent is this 1 over here. So 3 to the 1 is going to be equal to the argument. That's this x minus 8 times x minus 3. It's x squared minus 11x plus 24 divided by x. And to solve that, now it's kind of like a quadratic, but more like a rational equation. So to solve this rational equation, what I'm going to do is cross multiply. So 3 to the 1 is just 3, but I could write the 3 as a 3 over 1 and cross multiply to get 3x equals x squared minus 11x plus 24. And then subtract 3x from both sides to get 0, because we've got a quadratic. So review how to solve a quadratic, set it to 0. 0 equals x squared minus 14x plus 24. Factor it, x minus 2, x minus 12. And then set each factor to 0. So x minus 2 is 2. So x minus 2 equal to 0 gives us x equals 2. X minus 12 equal to 0 gives us x equals 12. Now don't be too quick to accept those answers, because looking at the domain, notice that the domain is only going to accept x's that are greater than 8. This x minus 8 has to be greater than 0. So x has to be greater than 8. So I'm going to have to throw out that 2, because if I put a 2 in for x, I'm going to get a negative value for the argument. Number 25. Number 25. I'm not sure what happened to number 25. It's missing. So let's write this out. Solve the equation, and we've got to start by condensing the log. So we have log, I'm not sure what this is written for. So let me see what's going on here. Let me just get a new page. So what I've got for this number 25, log of x plus 12 minus log of 2. So I could write that as a log, condensing it, log of x plus 12 divided by 2 equals log of 3x plus 5. Do you remember that? If the log of m equals the log of n, then m and n must be equal. So we could say that x plus 12 divided by 2 equals 3x plus 5. Using some cross multiplying to solve this, I could see that 3x plus 5 times 2. So I just did 2 times 3x plus 5, 6x plus 10 is equal to x plus 12 times 1. Solving for x, I'd have 5x equals 12 minus 10, and then x equals 2 over 5. And if you plug that in, you'd see that it does in fact come out correctly. Well, that wraps up our worksheet, and look at that, we did it in 32 minutes. Class would have been 50 minutes, but we sped through that quickly enough to get it done even quicker. So I hope that these examples make sense to you. If you don't understand any of these, would you please reach out to a tutor or send me an email, and I'd be happy to give you further explanation for any of these examples. But keep practicing, and if you struggled with some of these, try this. Take your learning into your own hands. Don't just say, oh, well, I just don't understand it. Tell yourself, I don't understand it yet, but then go back and rework these. Try from a clean paper. Pull out a clear paper you haven't written on yet. Try an example again. Try any of these again and see if you can get them on your own, practicing some of those procedures.